Gases and gas laws. Please notice at the top of your notes, you will find a place to write the difference between two very commonly confused words in this class. The first one is the one that we will use, and that is the plural of the form of the noun gas. And an example would be there are several gases that make up the air we breathe. One S in the center. For some reason, students like to put two S's in the center, but that's a verb. For example, the exterminator gases pests in a controlled area. So please know the difference. All right. You'll see a little chart where there are 5 variables, and you will fill in very specifically the abbreviation for each of the variables, okay, that we're going to be using to describe a gas during this unit. The amount of gas, small italicized n. Volume, capital V. Temperature, capital T. Pressure, capital P. And something called a gas constant, which is known as capital R. I'm going to show you how to use all of these in conjunction with each other and how they all relate to each other today. So the first one is the amount of gas. And we measure amounts as moles. Some people might measure amount as mass or volume, or, well, most people measure amount by sheer number, right? What's the amount of students in this classroom, or the amount of books in your personal library at your school, okay? So, or at your school. So we want moles to represent that amount, and that's can be given in mass over molar mass, or liters per molar volume. We'll talk about what those mean. All right, so what is the molar volume of a gas? And we're going to talk about this STP thing. No, it's not the stuff that you add to your gasoline to get out impurities. It means standard temperature and pressure. So, and I'm going to define what that means. So just hold on to that for a minute. This is a very important concept. 1 mole, starting right here, 1 mole of any gas. It could be helium, it could be diatomic chlorine, doesn't matter, okay? And you see helium is lighter than air, but chlorine is heavier than air, so helium will float and chlorine will sink. It doesn't matter what gas we're talking about. Any gas, 1 mole of it will occupy the same volume. That's pretty amazing. That's pretty cool. And that volume is 22.4 liters, okay? So 6.02 times 10 to the 23rd particles, 1 mole of any gas, will occupy the same 28.2 by 28.2 by 28.2 cubic area. All right? It could be a cube in a box, it could be a balloon shape, it doesn't matter. But that's important. All right, so what is STP? It is called standard temperature and pressure. And it's used because the volume of a gas varies with a change in temperature or a change in pressure. Once the temperature changes, once the pressure changes, the volume will change. You know this. You know this because you've had a basketball sit outside in the sun. I mentioned this in the last set of notes. And the sun will increase the temperature of the gas inside, and what happens? The volume of that basketball will increase. Why? Because the pressure increases. They're all related. So we'll get to more of that in a minute. So these are very important numbers that you have to remember. When you come up and ask me, I don't know what STP is, or what's the standard temperature, or what's the standard pressure, I'm going to tell you, go back to your notes, go back to your notes, go back to your notes. Because it's in your notes on slide 5. Here's slide 5, okay? STP. Standard temperature is 0 degrees Celsius, which we are going to have to convert to Kelvin all the time, and I'll show you how to do that soon. And standard pressure is equal to 1 atmosphere of pressure. That is the pressure of air pushing down on your head from space at sea level. Above sea level, that number will decrease. Below sea level, like if you were in Death Valley in California, it would be greater than 1. Okay? All right. So here's an example of how to use this information here. Okay, 1 mole occupies 22.4 liters. Okay, so how would you find the volume? And we're on slide 6. How would you find the volume at standard temperature and pressure of a gas if you were given moles or grams of that gas? If 1 mole of any gas occupies a volume of 22.4 liters, then all you need to do is set up a conversion factor. Whoa, here comes conversion factors again. They're quite useful. If one thing is equal to another, then you can use it to convert that one thing into the other, and vice versa. Just flip it over, the inverse, right? So let's say I wanted to convert 0.960 moles of methane gas into liters. I want to know how much volume of gas I have if I have this many moles, okay? Now you know that 1 mole occupies 22.4. This is just under 1 mole. So you know if I do any math at all, that my answer is going to be just under this number. And of course it is. So here's our conversion factor, 22.4 liters to 1 mole. I set it up with what I want on top. I want liters, so I put that at the numerator. And then I put that over 1 mole. Mole of methane cancels out. I multiply and I get 21.5 liters, and that's my answer. So now it's your job to practice. I'm going to give you 3 different, 2 moles and 1 grams, and you're going to, not now, but later, complete the answers to those questions, okay? I think that I show them to you, so I'm not going to show them to you, okay? Yeah, the answers do come up, so we'll move on to that. Okay, here's the next practice. Also, there's a place for this practice on your notes. So now you're going to go in reverse. So now you're going to take that conversion factor and flip it upside down, okay? So assuming, again, standard temperature and pressure, so you can ignore those numbers. How many moles are in these volumes? So you're going to multiply liters times 1 mole over 22.4, okay? All right. 2, the second variable, volume. Volume is the easiest thing to explain because we learned in the last unit that the volume of a gas is simply the volume of its container. There's not much more to say about that. Gases take up the volume of the container. Okay, let's move on to temperature. That was easy. Please note this. In red and bold, temperature must be in Kelvin when you do all mathematical calculations, okay? Temperature must be in Kelvin, otherwise your numbers will not work. So here's a comparison of Celsius to Kelvin. So 0 degrees is 270 Kelvin. Notice there's no degrees. 100 degrees Celsius is 373 Kelvin. So it's equal spread of numbers, but absolute Kelvin is based on absolute zero. Okay, that's why scientists use Kelvin, because it's based on that. It has no negative value because it starts at absolute zero, which is the theoretically absolute lowest temperature anything in the universe could possibly get to. So there's no negative. Motion completely stops at 0 Kelvin. We have never been able to obtain this in a laboratory setting, because there's always some form of heat traveling somewhere. But you get the point. So this is the important part of this slide, actually. This red up here, everything must be in Kelvin, all temperatures. And to convert back and forth, you simply add or subtract 273. So if I want Kelvin, I take my degrees Celsius and add 273. If I want degrees Celsius, I take my Kelvin and I subtract 273. Easy peasy. This is important to know. At any given temperature, the particles of all substances, regardless of their physical state, have the same average kinetic energy. Okay, at any given temperature. So I could have a glass of water. So the water is liquid, right? I could have that glass, that liquid in a glass, a literal like glass, silicon dioxide, like window glass, but you know, a drinking glass, sitting on top of a metal table, metal, like iron or aluminum, doesn't matter. Because it doesn't matter. Regardless of its physical state, the particles of all substances will have the same kinetic energy. So the liquid water, the glass, and the metal table, they'll all have the same kinetic energy. It's pretty cool. Okay, pressure. Gas pressure is defined as the force exerted by a gas per unit surface area of an object. And here, this is just pictures just showing you the difference between low pressure and high pressure, because you're reducing the volume. So you're making these particles closer together. So they're going to hit the walls of the container at a greater rate, which is going to make the force exerted by that gas over a smaller surface area, and so the pressure is going to go up. All right? All of those simultaneous collisions of billions of gas particles striking it increase the pressure. Now, if there are no gas particles, we remove them all, we suck them all out, there's going to be no collisions, and so there's no pressure. Such an empty space is called a vacuum. That's why they say the vacuum of space, like outer space. Very low pressure. So if we continue talking about pressure, here's a very important slide. The metric system unit for pressure is the Pascal, abbreviated capital P small a, but pressure is also measured in something called millimeters of mercury, abbreviated mmHg. Mercury like the element mercury, and atmospheres, which we discussed before. So if you want to convert between any of those, here are your conversion factors again. So if I wanted to convert from millimeters of mercury to atmospheres, I would use this conversion factor. If I wanted to convert from pascals to millimeters of mercury, I would use this conversion factor, and so on, and kilopascals, and so on and so forth, okay? So this is extremely important. That is why I have it in your notes, bold and large, so that you can always look back and refer to it when you're needing to convert. Because when you're doing calculations, both sides have to have the same unit of pressure. Otherwise, you'll get a number that you don't want. All right, so speaking of pressure conversions, here's some practice again. So you're going to do these again later. It's pretty straightforward by now. You just set up the proper conversion factor and you'll get from one to the other very easily. If you want to check the answers, feel free to come back to this PowerPoint presentation and just fast forward to slide 14, and then you'll have the answers for you, okay? All right. There's a law that's not quite in the other laws that we're going to discuss today, but it's called Dalton's law of partial pressures. The total pressure of several gases is equal to the partial pressures exerted by all those gases. So if I have several gases in an environment, in a container, each individual gas's pressure, I simply just add them up, and that would be the total pressure of all the gases present, okay? It's straightforward. There's not really too much thinking about that. Total pressure equals the pressure of all the gases combined. That's it. That's Dalton's law of partial pressures. There may be a question like this in some of your textbook work coming up, but we're probably not going to focus on that law too much. All right. These laws are the ones we're going to focus on. These other gas laws we're about to go over. They are mathematical representations of the observed relationships among those 5 variables that we just talked about: pressure, volume, temperature, moles, or quantity, and the gas constant, which you never have to figure out, which is a good thing. You're always given the gas constant. You just have to know which one to use, because there are 3 different ones. All right, here's the first one. Boyle's law. They'll have names. Boyle's law is the relationship between pressure and volume. Temperature is constant, so it doesn't really take part in the calculation, all right? So when the volume of a gas goes up, the pressure goes down. We mentioned that before, and you can see that in this animation. So here's the pressure pushing down, and then when the volume goes back up, the pressure also changes. So increased volume, decreased pressure, decreased volume, increased pressure. Squeezing pressure, okay, you're decreasing the volume, you're squeezing it, like when you crush a soda can or a balloon or something like that. You're increasing the pressure. That's the relationship. And this is the formula. P1V1 equals P2V2. These are important to know, but they're not overly important. Let's just say that if the question tells you that temperature is constant or amount of gas is constant, then we're going to use Boyle's law. But typically the question just says, if the pressure is this and the volume of this, afterwards, if you change the pressure to this, what will be the volume? And you just do the math and you solve for the missing variable. There will always be only one variable missing. Let me repeat that if you weren't listening. There will always be, in every problem, only one variable missing. If you don't see all the other variables, then you're needing to read the question better. Okay, I can promise you that, all right? And this little diagram is showing us how if you add weight up here, which pushes this down, you're decreasing the volume, you're increasing the pressure, okay? So you decrease the volume, pressure goes up. This is pressure down here going up, this is volume going down here, okay? All right. The next law is Charles's law, and that's the relationship between temperature and volume. This time, pressure is constant. So if we increase the temperature, we increase the volume. Again, we go back to our basketball in the sunlight, okay? Put that same basketball in cold air. Try it tonight. Try it at home. If you've got a ball filled with air, put it in the freezer and come back in an hour and look at it. It's pretty cool. And then go back outside and put it in the sun, and voila, it's going to be reinflated again. Nobody did anything to it. It's just that those particles inside are going bouncing, 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 and pushing on that ball, and they're going to make the volume increase. Okay. And this is the formula for Charles's law. So it's V1 over T1 equals V2 over T2. And note that temperature must always be in Kelvin. I state that again, like I did earlier. Pressure is constant, number of moles is constant. So if the problem says that they're constant or doesn't mention them at all, then we know that it is Charles's law. V1 over T1 equals V2 over T2. And again, this little diagram is showing you that you're increasing the temperature down here, okay? And so the volume is going to increase, but the pressure is remaining the same. And so is amount, okay? The next one is Gay-Lussac's law. This one deletes volume. Volume's kept constant. See how the volume of those two containers, this first one and this second one, are constant, okay? Volume's not changing, but the temperature changes in the second one. See, they lit a flame here, and so the pressure went up. And the formula is P1 over T1 equals P2 over T2. If temperature goes up, the pressure goes up. If temperature goes down, the pressure goes down. All right. And then we have the combined gas law. This is where you take those other laws that we just talked about and you combine them into a single law called the combined gas law. It's useful when none of the variables are constant. It's useful when all of them are changing. Again, temperature must be in Kelvin, and any units will work for pressure or volume as long as they are consistent. So I don't have to have liters here. I can have milliliters here, but I must use milliliters here. And I don't have to have atmospheres here. I can have millimeters of mercury here, but then I also must have millimeters of mercury here for pressure. And again, temperature must be in Kelvin. So it's P1 V1 over T1 equals P2 V2 over T2. Sorry, said it too fast. So it's very useful when all of the variables are constant. We're going to see that. All right, and the final gas law, the last one we're going to talk about today, is the ideal gas law. And this is the only equation in which the amount of gas, N, number of moles, is considered. So anytime a question asks you about the amount of gas, and they could also give you grams as well, because you know, based on stoichiometry, how to convert grams into moles. You could easily convert it into moles and then solve for any of the missing variables here: pressure, volume, or temperature, okay, or moles. But notice volume. Make sure you mark this in your notes. Volume in this case must always be liters. And here, volume could be liters, milliliters, deciliters, centiliters, kiloliters, it doesn't matter. But here it has to be in liters. So if you have a question that's talking to you about moles and they give you the volume in milliliters, you have to convert it to liters first, okay? Otherwise you can get the wrong answer. And this is the gas constants, okay? R are the gas constants. So there are 3 different ones, and you must use the one that corresponds to the pressure. So if your pressure is in atmospheres, you have to use this first one. If 0.0821, if your pressure is in kilopascals, you have to use this value for R. And if your pressure is in millimeters of mercury, you must use 62.4. So that's here. If your pressure, this pressure here can be in any of those units, millimeters of mercury, kilopascals, or atmospheres, your R value, your R gas constant, has to match that pressure unit, okay? If not, you're not going to get the right answer. So this is very important to have in your notes. So put a little asterisk next to it, highlight it, whatever, okay? So what is an ideal gas? why do I use an ideal gas law? That seems like a very strange thing. What makes a gas ideal? Well, we know that oxygen is ideal for humans and other living organisms to live, but that's not what we mean. Ideal meaning mathematically, it's easy to work out, okay? So we have to imagine a gas that's not affected by outside influences, so to speak, okay? So here are the things, the bullet points that make an ideal gas an ideal gas. Particles, they take up no space. They have no intermolecular attractive forces. They're not attracted or repelled by the wall of their container. Now we know, of course, this doesn't happen all the time, but for mathematical purposes, this is what we're doing. Constant random motion in straight lines until colliding with the walls of the container. And then the collisions are perfectly elastic. And we talked about that in the last set of notes. Therefore, kinetic energy does not change. But we know that that is not reality. But still, in an ideal situation, all of this would work out. And for the most part, many situations are close to ideal. So that's what we're working with here. Many situations in reality. Okay, so how do we, this is something, a task that is just a mathematical puzzle, so to speak. And it's deriving the different gas laws from the ideal gas law, okay? And this is right out of your textbook. Whenever you see a picture like this, it's right out of your textbook. I took a picture with my phone and I sent it to myself on email, and I copied it and pasted it into your notes for ease of explanation, okay? So if you master the following strategy of being able to isolate variables, okay, you can derive all of those gas laws, Boyle's, Gay-Lussac, Charles, from the ideal gas law. Consider the example of a fixed amount of gas held at a constant pressure. You need Charles's law to solve problems involving volume and temperature. So if you don't remember what Charles's law is, you can derive it by deleting the variables that you don't need. Now, many of you are going to have to come back to this or look in your textbook under gas laws and find this, okay? So using the ideal gas law, you write two equations, 1, 2, okay? And you label them appropriately. All right, well, you just look at this and look at this is labeled, okay? The quantities that don't change are shown in red. P, N, and R. So those are constant, so those are going to cancel out. You isolate the volume and the temperature, the two conditions that vary, on the same side of each equation. So here, I've done it for you here, okay? So you can see that when you do that, you get V1 T1 equals nRP, and V2 T2 equals nRP. Well, if A is equal to C and B is equal to C, then A must equal B. I know you know that rule in math and its name, okay? But just remember that that is this rule. Okay, so all you're doing is isolating variables, canceling out the ones you don't need on both sides, and then looking at the relationship between the two, and you end up with your final. So practice doing that. I've done it for you for Charles's law here. Practice doing the same thing for both Boyle's and Gay-Lussac's laws on your notes, okay? All right, and I actually have the answers right there. So you'll have to go back to your PowerPoint presentation link to look at your answers and compare them. Okay, So do that later. So what are some situations where the ideal gases do not behave like ideal gases? So these mathematical equations will not work in certain situations, which luckily we don't have to worry about in this class. So we just have to know what those situations are. So when you have some extreme pressure, the ideal gas law won't work. If you have extreme temperature, if you have a polar gas like water vapor, or large gases like this butane here. Butane is the fuel that's found in barbecue lighters, okay? Not barbecue tanks, that's propane. The lighter itself, the little handheld lighter that goes click, click, click. Okay, that's what I mean. So these four situations would make an ideal gas not an ideal gas. All right. So it says time for practice sheet. You're going to go back simply, and the practice sheets will be coming on Monday and Tuesday. You'll have 2 days to work on those. But right now you're going to go back into your notes here and complete those practice problems. Okay? The end.